All right. In previous videos, we learned how to map a large part of the radio sky, about 1% of the sky in a single map. We learned how to turn that map into an image, making the invisible universe visible. We talked about typical sources of radio emission, what we might expect to find in our part of the sky. Now, in this video, we're going to go see what's there. So I'm in Astromancer. I'm in the radio source finder, and I've already loaded up one of the maps. This happens to be map 68, but you will have your own map. Some have a lot in them, some have just a few things in them. And we're going to try to find as much as we possibly can and identify as much as we possibly can using this tool. So we have a number of controls around the edge of the image. The first is scale. It's basically adjusting the color palette. If I slide it to the right, I get more colors. Maybe if I go too far, everything looks the same shade of red, but not far enough. I'm not using as many colors. So I try to pick something that gives me a lot of definition so I can see the sources more easily. It's arbitrary. It's up to you. Whatever works best to help you find the sources. Over here, we have a zoom. I normally like to shrink it so I can see the whole map. Something like that. And then next, we're going to fix the WCS. Now, in the optical images, Skynet uses the background stars to figure out where the map is in the sky and get a really good coordinate system on the image. These images have a coordinate system. If I look down here, it's in galactic longitude and latitude in this particular case, but the system is not very good. It's just based on where we were trying to look. We want to zero it in. So just like in the optical where you use background stars, background sources of emission of known position, we're going to do the same thing here. You'll see a few circles on your map. These are famous radio sources. They're famous at some radio frequency. It may not be the radio frequency you're working at. Some of the circles may not line up with emission in your map, but most of the time they do. So we're going to use the sliders to line them up with the sources, get as many as you can. And try to do it as accurately as you can. It's really important to be as accurate as you can because we're about to click on parts of this map and load up optical information. But remember, these radio maps are huge, and the beams, these circles are 2 beam widths across. That's a huge chunk of the sky. Each of these circles is like a degree or so. And so they really need to be accurate for your coordinates to be accurate. And when you explore, you're going to have to really hit the center of the emission, whether it's circled or not, to bring up the right part of the optical sky, because the optical sky is not blurred like this. Okay, and then we can start exploring. The obvious thing to check is this. It's the brightest thing in the map. If I click on it, it puts crosshairs, and I may move my mouse around and try to get those crosshairs as close to the center as I possibly can, something like that. And if it's a circled source, it will pull up some information over here. It has its radio name. Most of these are 3C sources. There are Parkes sources. There are NRAO sources. But it has the radio name, and it may have a link which will take you to Simbad. Not the main way we're going to use Simbad, but it tells you what this is. Cygnus A, it's a Seyfert 2 galaxy. So that's one of our types of radio galaxies. It gives you a plot here of how bright it is at different frequencies. Our frequency is mapped with this dashed line. It says here, we're observing from 1355 to 1435. It pulled that information out of the file when we loaded it in. And it fits all the data that it has in its database. And it says that our source at our observed frequency should be about 1600 Janskis. It's something we can check later, but that's quite bright. Now, what I'm going to do is, once you click here, get it centered really nicely, you can query. And this will load Simbad for that part of the sky. If it's a busy part of the sky, it may take a moment. So when Simbad loads, it has a list of sources, and it has an optical picture, and it has all the sources marked on the optical picture. Now, we are searching 1/4 of a beam width. In our radio map, our telescope has a beam width, and we're going to search over 1/4 of that, which in this case is 13 arc minutes in radius. That's a big chunk of the sky, in the optical anyway. And there's a lot going on there. And that's why we have so many sources in our image and in our table. So how do we sort through this mess to figure out what we're looking at? What is our radio source out of all these possibilities? Well, a couple hints. First thing you'll want to do, slide over, click on references, and the closer you get to the center of the galaxy, there's going to be more and more stuff in your table, and the sorting process will be slower and slower. Then click on it again. So we get the largest numbers at the top. These are sources that have been written about a lot. This source has 2,443 references. It's probably what we're interested in. Slide over, and it says Cygnus A. Okay. It says name. So if it says name, it usually means it's a very popular source. It's giving its popular or standard name. And then you can copy that, open up a new browser tab, and search on it. Find articles about it, find the Wikipedia page about it. If it's a popular source, it probably has a Wikipedia page, and you can learn more about it. Okay, let's see what else. Let's try something that's not circled. You can check all these circled points, but also every bright spot, you and your teammates should divide and conquer and basically hit all the bright spots. All these faint things here, that's probably noise. But above the noise level, it's probably something. You're not always going to succeed, but I'm not even sure what this is. I'm just going to check it out. I'm hitting the query. All right. Let's sort by number of references. Click once, click twice. Not nearly as many references as before, so this is not as popular, as common of an object. But if we slide back here, we can usually figure out what it is. So, two things that we're looking for: the object type and the identifier. Let me load up this page of notes. So as mentioned in the previous video, object types to look for. In the case of star-forming regions, Bremsstrahlung emitters, the most likely designation will be H2, if it's an H2 region, a hydrogen ionized region. Though sometimes you'll also see SFR for star-forming region. If it's hidden by a lot of dust, you may see DNE, dark nebula, or dark nebulae, plural. What else? If it's a supernova remnant, you'll see SNR. And if it's a supermassive black hole, the core of some other galaxy, it could have a variety of designations, such as AGN, QSO, SY1, SY2 for Seyfert galaxies, little RG for radio galaxies. So those are the kinds of things that we're looking for, though there could be others. Sometimes it just says RAD for radio source. It means the professionals don't know what it is. It's just something emitting radio. We don't know what. Now, if you see an asterisk, that means star. And as we mentioned in the previous video, stars, at least other than our sun, due to its close proximity, we can see it very bright, but other stars farther away, we're not going to be able to see that in the radio. So anything with an asterisk we can dismiss. And right here, the second and third things in the list are H2 region. They're both probably referring to the same thing. It just has different names in different catalogs. Now, under identifier, these are the objects, their names, their designations, things to look for. As we already said, if it says name, it's something really common. Otherwise, you can look for an M. This means it's part of the Messier catalog. Those are the biggest, brightest things in the sky, typically. Very famous. NGC, those are quite popular, quite common. If it has an NGC designation, you can copy that, put it in a browser tab, Google, look at Wikipedia, you'll find information. Now, a little bit less common, but you can still search on these things, LBN. It's Lin's Catalog of Bright Nebulae, or SH, the Sharpless Catalog of H2 regions. And you can see right here we have an SH, SH289. Click on this here, and it's just going to tell us it's an H2 region. It has some radio emission. So we can open up a new tab and just search on its designation. And you can see there are pages that will take you to more information about it. Okay, and you can keep plugging through here. There are probably, I don't know, close to a dozen things in that map. Some have less, some have more. This is one that probably has more. Now, the maps closer to the center of the galaxy will be trickier. So this is map 8. This is the map that's closest to the center. In fact, this right here is the center of the galaxy. So let's poke at this one a little bit to see how things might be different. The problem is in map 8 and 28 and somewhat in 48, there's so many sources that they are blurred together. They are on top of each other. Adjust the zoom. Going to adjust the WCS. There's obviously something here. Maybe I'll move it down a little bit. I can use that source more reliably to fix the WCS than this because it's blurred with everything else. Let's click on this first. This should be the center of the galaxy. Try to get those crosshairs close to the middle as possible. Query it. This one may take a moment because it's very busy there in the center of the galaxy. Going to be a ton of sources. While that's loading in, I might pick something else. Here's a bright spot. It's not circled. May have some luck there. That's still loading. Center of the galaxy, very busy. I'll get this query going at the same time. Check out this one as well. Here it is, the one at the center of the galaxy. Sort based on the reference number, sort again. 15,000 sources, galactic center. Okay. And you can explore from there. Close that one. Our next one was this region over here. You can barely see it merged with everything else, but there's kind of a bright spot. There's a bright spot there. You'll want to explore. So we did this one. Here it is. And clearly there's some stuff going on here. Now, when you're working in the center of the galaxy, sometimes you'll find a big, bright nebular region. And we're not covering the whole nebula. We'll try, but we may have to expand our radius here to cover the whole nebula to get a good identification, but we'll see. 16,000 references for NGC 6618. There's M17. So Messier 17, 6618 is probably the same thing. The Omega Nebula, big popular astrophotography target. Come back over here to the list. OPC, that means open cluster. Those are just the stars, but right underneath it, we see star forming region. Down here, we see H2 region, both connected to M17. Okay. Now, often when you're probing in here, you may not see anything big and bright because it may be hidden behind a lot of dust. And again, if you don't find anything, this time we lucked out. The spot designating this as the Omega Nebula was within our search radius, but if your region is bigger than your search radius, you can double it and submit the query and do the analysis over that larger region. Or if you had a hard time setting your WCS, if you didn't have a great number of points to work with, you may want to search over a larger region because your WCS may be inaccurate. So there are a couple reasons why you may want to search over a larger radius, though it will be slower. Okay, this one up here. Here we go. Nothing big and bright. What is this? Click on references, click again. 822, so there's something popular in here. It's a supernova remnant, and in fact, it's Kepler's. It's the one Kepler discovered back in 16 something or other. Yeah. Yeah, Kepler supernova remnant. Seeing if the dates here escapes my memory at the moment, but again, you can put that into a browser search and learn more about the target. Okay, enough examples. Now, just a few final things. As you're exploring your image, you're going to want to record what you find. And so in the guide, you can link to a source catalog where you and the other teams in your class can start filling in information. This is my current class's source catalog. You have the various maps here, team name here, source finder name. So if it's circled, that's the designation right here. Source finder flux density, either estimated or at 1400 megahertz. So, well, let's start with this one. This has a lot of flux information. It will estimate the brightness at our observed frequency, which is around 1400. But not all of them have that much information. Sometimes there may just be one point, but if that point's at 1400, then you can get the flux information there. Like this one is 75 Janskis. And you'll put that information here if it's available, if it's a circled source, because you'll be able to compare that to your own measurement in just a little bit. The galactic longitude and latitude that you searched. So when I clicked here, down here, you have the galactic longitude and latitude of the search. The Sinbad name, once you figured out what it is, such as here's Kepler supernova, you can enter that here. The right ascension and declination, once you figure out what something is in Sinbad, go back to the table here, sort, Kepler supernova, here's the right ascension and declination. Put that in the table. The object type, this is a supernova remnant. There it is, SNR. And any other notes. If you ran into any difficulties, either with Sinbad or issues with the map, such as we discussed in earlier videos, you can designate that here as well. The rest of this table is for your own photometry measurements. Come back to that in the next video. Oh, and just finally, so you know, there are a few more buttons here. Download will green capture. You can type your name in there. Honor code pledge. And that's one way you can get figures to go into your blog. Also, we have a button down here to save the FITS file. We will soon have two buttons. This button saves the full FITS file, all the layers that are typically in a radio FITS file. We're also going to have a button to save just the main layer. So it's smaller and easier to load into Afterglow. One of the activities that we'll do near the end of this module is we'll take everyone's maps, load them all into Afterglow, and make a mega map. But it's easier if the files are smaller. And so this way you can save just that one layer, resulting in a smaller file. And the advantage of saving it here is when you save it with either of the buttons, you'll be saving the corrected WCS. When you recentered the circles and fixed the WCS, that will now be written into the FITS file. So when we upload it into Afterglow, it will have a correct WCS. So when we stitch them all together into the mega map, everything will be in the right position to start with. Okay, we'll stop there.